Hi, so today we will be going through explicit differentiation. Now, what makes explicit differentiation good is that it is a lot simpler to do than by first principles. Because you don't have to do all those calculations and stuff. You just have to remember this formula. So we say we have a function y is equal to ax to the power of n. The differentiation of this dy dx is equal to a times by n x times by x to the n minus 1, right? Let me just put a dot there to show multiplication. And that is a lot simpler. So let's say we had y is equal to 2x to the power of 3, right? The differentiation of this according to this would be, so a is the 2 in this instance, and n is the 3. So we got a times by n, so 2 times by 3 is 6, x to the n minus 1, n is 3, so 3 minus 1 is 2, 6x squared. And that would be our answer, right? Now we can compare this to the by first principles to see if it's the same. So by first principles, it would be the limit as h tends to 0 for 2x plus h cubed minus 2x cubed over h. So let's expand the brackets up here. So we got 2. So this is going to do x plus h times x plus h. So that's x squared plus 2x h plus h squared. And we still got x plus h. Just breaking it down to make it easier to calculate. Minus 2x cubed all over h. And the limit as h tends to 0 of 2x cubed plus 2x squared h plus xh squared plus xh squared plus 2xh squared. Yeah, xh squared, 2xh squared plus xh cubed plus h cubed, sorry, minus 2x cubed turns to over h. So we're going to simplify this. So you got 2x cubed plus, so you got how many x squares do we have? Just one. So we got 2x squared, so that's 4x squared. Got xh squared plus xh squared, that's 2xh squared, times by 2, so that's 4xh squared. Oh yeah, and sorry, we got xh squared plus 2x squared h, sorry, that should be 2x squared h, xh squared, yeah, hx squared, yeah, hx squared. So that should be hx squared, h squared plus 2x hx squared, yeah, 2x h squared, yeah, h cubed, yeah, okay. So 2x cubed, you got 2x squared h, and there's another one there. So you got 3x squared h, put the h down so they look the same. And so we now have times by 2 is 6x squared h. No, 6x squared h, right? And this one, you can, okay, 2x cubed plus 6 squared h. And we have x h squared. And we have 2x squared, so that's 3x squared, 6x squared plus 2h cubed minus 2x all over h. Now I'm going to simplify. So 2x cubed minus 2x cubed is 0, divided by h. So get rid of the h there, get rid of that one h there, this the h there. So then we have limit as h tends to 0 for 6x squared plus 6x h plus 2h squared. And as h tends to 0, this becomes 0. So then we get left with 6x squared, which is the same as we had with the other one. Now you can see this is very long-winded. The other way is so much simpler. So if you're not asked to differentiate by first principles, your go-to is explicit differentiation. It is significantly faster. So let's try another example. Now, you need to also be aware that whenever, let's say we had an equation, let's give a general one, ax to the n again, but let's say it's plus c, where c is a constant, right? It's just a number. What do you think the dy dx would be in this case? Well, it would be in fact be a times n to the x, n minus 1. And why is that? That is because in the case where c is a constant, right? C is the same as cx to 0, because x to the power of 0 is equal to 1. So it's the same thing. So now if we, so let's say we had another expression, let's call it z, just make it different. So we had an expression z is equal to cx naught and dz dx. So why dz? Because it's with respect to, we were differentiating with respect to x, and the function is z. So it's not y because the function isn't y. That's why it's different. So So essentially we're going to do the same thing as we would do. So you'd have c times by 0, which is n, times by x to minus 1, that's 0 minus 1, and that would just all equal to 0. So that's why we have every constant as 0. All right, let's just highlight this here. So I'm just going to show a quick example with this. So let's say we had a function dy, so function y is equal to 2. What would the differentiation be? Correct, it would be 0 because there's nothing there. And as you can see an example as well, I did the plus sign. So with differentiation, we can have the addition rule, right? So essentially, that is when you have a function, let's say 2x squared plus 3x, right? Because they're added together, differentiation of everything altogether is the same as if you had two separate functions to differentiate them individually. So, for example, the differentiation of this one, the first one is 4x, and the differentiation of the next one is 3, right? So if you have a function where you have, x squared plus x cubed, you can in fact differentiate each one and keep the addition or subtraction signs is the same if there's subtraction as well. So let's say you had y is equal to 4x to the 3 minus 2x squared. Right, dy dx would be 3 times 4 is 12. 3 take away 1 is 2, so to the power of 2 minus 2 times 2 is minus 4. There's the minus sign there already. 2 minus 1 is 1. We don't have to put the 1 there. So it's 12x squared minus 4x. All right. So now there are some other forms that we have to pay attention to as well. So you can also have a function where, let's say, x is to the power of a negative number, or x is in the form of a fraction. So if you remember how powers work, right, and let's separate these two, right? So in each case, we would have this is the same as saying a over x to the n, right? Because if you were to have a question, you may be in this format, right? But it's the same as this. So if a power is in a fraction, so for example, x to the n is a denominator, it's the same as the numerator times by x to the negative n. And with y is equal to ax to the power of n over m, this is the same as y is equal to a times by the m root of x to the n. It's the same thing, right? So now let's say we had questions based on these two. So let's say we had an equation y is equal to 2 over x squared, right? So rewriting this out, we have 2 times by x to the minus 2. Now applying the formula, the same one from earlier. Yeah. So using this formula, what would we do? So you have a times by n, so 2 times by minus 2. So y is equal to minus 4 and times by x to n minus 1. So n is minus 2. So minus 2 minus 1 is minus 3. So minus 4x to the minus 3, which is the same as saying minus 4 over x to the power of 3. It would be equivalent, right? So that's how you do an answer question like that. So now let's say we had one of the other examples. So let's say we had y is equal to 3 times by 5 roots, 5 to the 5th root of x to the power of 8, right? So in this example, again, we can rearrange this. This can be rewritten as 3x to the power of 8 over 5, right? So again, let's apply the formula. So dy, sorry, this would be dy dx. So dy dx is equal to a times by n, so 3 times by 8 over 5, that's 24 over 5, times by x. So n minus 1, 8 over 5 minus 1. That's same as 8 over 5 minus 5 over 5. So that gives us 3 over 5. And that would be our answer. Again, you could rewrite this as 24 over 5, 5 to the root of x to the power of 3. Right, they're equivalent answers, they're the same thing. So thank you for listening. I hope you remember the formula for explicit differentiation, and hope to see you next time.